let's get started. Hey, everyone. My name is Kelvin, and in this session, I'm going to talk about motion planning and controls. And before we dive into the details of motion planning and controls, let's revisit how they fit into the broader autonomy stack. So if we were to take a look at a traditional autonomy stack, you'll see something like a cascade of different modules from perception, prediction to planning to controls. And this has the advantage that the stack is very interpretable, and there's a very clear separation of responsibilities in between each of the modules in the stack. However, these systems typically have very narrow interfaces in between each of the modules. So you have really little information propagation in between them. And each of these modules are also typically optimized independently. And so each improvement to each submodule does not always translate to improvements in sort of like the broader system. So what we really want to be able to do is to train this entire system with the end task in mind, right? So as Sergio probably mentioned earlier today, on the other side of the spectrum towards this goal, we have these black box end-to-end approaches where we can replace all the modules of a traditional stack with a single black box neural network. Now, this approach solves a lot of the problems that we just saw with the previous one. It eliminates sort of the narrow interfaces in between independent modules, and it allows us to train neural networks that end-to-end optimize for the end task, right? However, with this black box approach, we lose interpretability. And this makes it really difficult for both developers to like understand, debug, and improve the system, as well as it makes it really difficult for systems engineers to validate and verify the safety of this like tremendously complex system, right? So the natural question to ask then is, can we get the best of both worlds? And as you can probably guess, we think the answer is yes, by building these interpretable end-to-end autonomy stacks. And as before, the overall system is still modular and interpretable. So you still have perception and prediction, predicting these intermediate representations of how the world looks like and how it would evolve over time. But now you have these, but now the interfaces in between each of these modules are made significantly more broad, thus allowing information and uncertainty to propagate throughout the entire system. And moreover, the full system is now end-to-end trainable through motion planning and controls to optimize for the end task, right? So in this session, we're going to cover some topics and recent research on how we can learn these interpretable end-to-end systems from the perspective of motion planning and controls. So in the next like 30, 40 minutes, we're going to cover the different inputs and outputs to such a system, how we can train these systems, right? How we can design an interpretable end-to-end autonomy stack. And we'll also touch a little bit on how to design the system so that it can react and interact with other traffic participants more naturally. And then finally, we'll go over some of the main ways we can then convert the system's motion plan into actual control commands that we can then send to the vehicle to make it move. So let's get started with inputs. So one of the most natural inputs to an end-to-end motion planner is raw sensor data. We've already covered sort of the various sensors on a self-driving vehicle in detail in the previous session. So here I'll just do a quick rundown of some of the more common sensor modalities being used. So first one being camera. It's among one of the most popular input modalities because they're cheap, can capture high resolution images of the world with rich textures and fine details, but they lack depth information, so we can't get 3D geometry right off the bat. LiDAR point clouds are another popular modality. So compared to camera, they give us really accurate 3D geometry. And what that allows us to do is build these, is to use this information to directly identify where's the free space in the world, where are the occlusion regions in the world around the self-driving vehicle. And as you can imagine, this can be really useful for planning a safe maneuver. Moreover, LiDAR is also more robust to lighting conditions than camera, and but they lack sort of the texture and the fine details captured by camera images. And then finally, another popular sensor is radar, which can give us radial distance and velocity measurements. Compared to LiDAR, radar can help us capture much longer range information, but they're generally more lower resolution than LiDAR and suffer from various different kinds of artifacts. So now it should be clear from this discussion that these different sensor modalities are not mutually exclusive, but in fact complementary to each other. since they capture different kinds of information and have different kinds of performance characteristics, right? So this is raw sensor data. Another source of inputs are the intermediate representations coming from upstream modules like perception and prediction. So this can be in the form of like coarse bounding boxes, right? Or occupancies, which tell you like which parts of the world are free space versus occupied, as we learned in the previous session. And then, or it can just be like a set of affordances or costs. Like, for example, what is the distance of the self-driving vehicle to its nearest actors, right? So these intermediate representations are more lightweight than raw sensor data. So this allows us to design more efficient methods or models to process these inputs. However, you would lose some of the details present in raw sensor data, and there are still other artifacts that you would need to handle. For example, like what happens if detections flicker a little bit over time, right? Cool. Yeah, next is HD maps. This is another super useful input modality to end-to-end motion planning because it gives us a really good prior on where the SDV can drive, right? How it can reach its destination, or the kinds of traffic rules around the SDV, et cetera. And this can be represented in various ways. For example, we can have rasterized images. We can represent it as lane graphs, or again, as a set of affordances. For example, like the distance to the center line of the self-driving vehicle, or how far it is to the upcoming stop sign, right? So each of these representations have their own pros and cons. For example, rasterization is super simple and can be easily processed by CNNs. But the features extracted generally have limited reception fields, and it's really difficult to encode priors into your motion planner, like saying, I want you to drive along the center line using rasterized maps. And you'll just need to sort of hope that your model has learned to do this, right? On the flip side, affordances make it much easier to encode these priors, but then it requires manual feature engineering to determine sort of like which affordances you would actually want to give to the model and how you could actually compute them. Right. And then finally, another super important input to motion planning is the intention of the self-driving vehicle, because ideally we'd like our self-driving vehicle to actually drive to some destination rather than just like go around and randomly, right? So these are usually, this intention is typically represented as routes, which can be a sequence of lanes, or maybe we can just extract a sequence of commands from the routes. So for example, we can say like in the upcoming intersection, you want to make a right turn. Cool. So that covers inputs. Next, we'll take a look at several different output representations for an end-to-end motion planner. So one of the most straightforward ways is to have the motion planner directly predict steering and acceleration. Another approach is we might have the model predict a trajectory of waypoints representing sort of where we expect the ego vehicle to be in the future, right, over time. And then we can use a very simple controller like a PID controller to then generate a sequence of steering and acceleration commands to track that trajectory. Now, both of these representations are super simple, and they're pretty well studied in the literature. However, it's really difficult for us to encode prior knowledge into the model with these output representations. And it's also very difficult for us to interpret why the model would choose to output a particular acceleration or steering value versus some other ones, right? So an alternative representation that is more interpretable is to predict the cost of a trajectory. So this follows sort of the idea from traditional planning approaches, where you have some objective function that measures the goodness of a trajectory, and then you want to find a trajectory that then minimizes that objective function. So here, instead of writing that objective function manually, you would learn to predict that objective function instead, right? Then once you have this cost function, we can then sample a bunch of trajectories, compute the cost of each of those trajectories, and then we can pick the one with the minimum cost to use as our motion plan to execute. So for example, here in this figure, we're depicting a spatial temporal cost volume that's predicted by the neural motion planner, and each voxel in this in this volume basically represents the cost of the SDB being in that particular location at that particular time, right? So you can use this cost volume to then cost a bunch of trajectories and determine the best trajectory to execute. Now, the strength of this approach is that once you have this, it's very easy for you to encode prior knowledge into the system. So, for example, if you have constraints about avoiding collision, for example, right? We can just add those as additional costs on top of the learned costs that we have in order to encourage avoiding collision. However, usually we don't have ground truth costs that we can use to directly supervise a model to predict them. So then we'll need to come up with different learning objectives, and this usually makes training a little bit more challenging than usual. Right? Yeah, and besides these two main representations, there are also a couple other possibilities as well. So for example, we can predict a set of affordances, like the SDV's distance to its nearest center line or distance to its nearest actors. And then these affordances could directly be used by a controller to determine actuation commands. Or we can also train the end-to-end motion planner to perform auxiliary tasks like object detection, segmentation, depth completion, or optical flow. And these auxiliary tasks not only improve interpretability, because now we can see like sort of what the model is observing, but it also helps the model learn better feature representations that would ultimately result in better planning. Cool. So we've covered inputs and outputs. Next, let's talk a little bit about how we can actually learn these kinds of models. So one of the most straightforward ways to do this is via open loop learning. So in open loop learning, the policy's actions are never actually executed during training. So it never has a chance to observe the consequences of its actions during training. And one of the most common ways to do open loop learning is behavior cloning. So here the model observes expert states, and it simply tries to imitate the expert's actions. So the loss function for supervising such a model is can be as simple as a L2 loss between the predicted and ground truth controls. Or if you're using something like a cost-based planner, we can use like a max margin objective that encourages the model to cost non-expert trajectories, like trajectories that it rolled out itself, to be higher than the expert trajectories. For example, any trajectories that you collected from a human expert driver, right? Now, the strength of this approach is it's very simple, right? And it's very easy, and it typically has pretty high sample efficiency. However, because the model's actions are never actually executed during training, it will only ever observe expert states during training, not the states that it would see had it actually followed its own actions, right? And what this means is that this leads to a distribution shift between training and inference. So when you're actually deploying the model during inference time, the model will actually plan out actions and it would execute its actions either in the real world or in simulation, right? And it would potentially make mistakes and encounter states that it would have never seen before during training. And these mistakes can compound over time, leading to sort of catastrophic errors. So this creates a distribution shift between training and inference, and it's typically why open loop learning suffers from problems when you sort of try to deploy it to a closed loop setting. Now, typically there's ways to alleviate this issue using data augmentation, right? But the fundamental problem of distribution shift still occurs if you're using open loop learning. Yeah, so on the other hand, to address this issue, you can use closed loop learning. And in closed loop learning, the policy now actually gets to execute its actions during training, and it will actually see sort of the states induced by following its own actions during training as well. So compared to open loop learning, there's now no distribution shift between training and inference anymore, because in closed loop learning, you're actually executing your actions, right? However, to actually do closed loop learning, we'll need some way for the model to actually execute its actions. And we will either have to do this in the real world or using a really realistic simulator. And once this prerequisite is satisfied, then the question is, how do you supervise a model in these now unseen, new unseen states that we might not have potentially collected data for, right? So the first approach we'll discuss, it makes use of an interactive expert for that purpose. So for example, in dataset aggregation or Dagger, during each iteration of training, we'll unroll the learner policy in the environment many times, and then we'll query an interactive expert to help us label the states visited by the learner policy with optimal actions. And then finally, we're going to retrain the learner policy on these new state expert action pairs and repeat this process many times until convergence. This allows us to supervise the policy with expert actions, even in out of distribution states. However, interactive experts are often unavailable, right? Or they can be prohibitively expensive to include inside the training loop. So what can we do if we don't have an expert? Another approach is maybe we can design and train a privilege policy and then distill this privilege policy into the learner policy. So for example, we might train a privilege policy that has access to ground truth simulation state information, right? And then use this policy to supervise a learner policy that only has access to raw sensor data. Now, the reason why this might work is that the privileged policy then can act as sort of an expert to supervise the learner in the same way like we use an interactive expert in Dagger. However, in this approach, the learner policy is now upper bounded by the performance of a potentially suboptimal expert, right? So designing a good privilege policy here is really important. Now, if we don't have access to an interactive expert, we can also use reinforcement learning to train the learner policy with explicit reward functions and closed loop. So again, this can be done in the real world, which eliminates the possibility of a sim to real domain gap, but it's difficult to scale this safely. Or we can also do this in simulation instead. In this case, having really realistic simulations is really important to minimize the sim to real domain gap, right? And we'll see in later sessions how we can actually do this. And even then, the sample efficiency of these approaches can be prohibitively low, right? So one way to improve sample efficiency then is to use approximate, so how can we actually improve sample efficiency then? One possibility is we can use approximate world models instead to make simulation more efficient. So for example, rather than simulating all the behaviors of all the agents around you and how they would react to your actions, maybe we'll just put the world on rails and make the simulation non-reactive to what we do, right? Another approach is we can actually improve sample efficiency by changing the model's action space instead. So while in typical RL models, you would output sort of control commands directly, this approach actually makes learning long horizon or long-term reasoning a little bit more difficult. So instead, we can learn models that reason and plan in, say, trajectory space instead, and this makes it easier to learn about long-term reasoning. The composition of scenarios that we train on is also extremely important for sample efficiency. So for example, by incorporating long target safety critical scenarios into training and scaling up the diversity of the behaviors that we observe in our scenarios during training, we can actually train motion planners that way more efficiently and to better performance than training on sort of nominal scenarios collected from the real world alone, right? And then finally, incorporating real data and combining imitation learning to RL is another promising way to address some of the shortcomings of reinforcement learning. So for example, we can directly use imitation learning pre-trained policy to initialize the RL agent. And this would hopefully make the initial exploration by the RL agent more efficient. Alternatively, we can also just use a sparse reward function in the RL part and combine that with a very, very dense imitation learning loss so that we can learn more realistic driving policies without the need to manually tune reward functions and manually shape them. Okay, and then finally, we've sort of seen how the composition of data plays a big role in learning these end-to-end motion planners. So another question to ask then is how can we sort of leverage internet scale data and foundation models for self-driving as well? And this has been the topic of several recent papers. For example, in driver agent on the left, on your left, driver agent combines LLMs with chain of thought prompting and tool use in order to predict a motion plan for the self-driving vehicle. So the LLM is instructed to sort of act as the brain for the self-driving vehicle. And then it's asked to use tools like perception or prediction in order to help it reason about the scene, and then ultimately generate a trajectory for the self-driving vehicle. Now, the LLM here doesn't actually have access to the raw sensor data. Instead, it relies on sort of textual descriptions of critical objects around the self-driving vehicle that it got by invoking these perception or prediction tools, right? So to address sort of the potential loss of information in this approach, we can also learn adapters that project visual tokens directly into the LLM's embedding space, enabling the LLM to sort of see the raw sensor data directly. And if we take this one step further, actually, we can just directly use a pre-trained VLM, right, to reason about or to see the raw sensor data directly, bypassing the need to learn such adapters, right? Now, obviously, we're still sort of in the early days for how to use these foundation models for motion planning, but this is definitely a very exciting line of research that could open up many possibilities for building more capable end-to-end self-driving systems, right? Okay, so that wraps up learning. And next, we'll talk a little bit about how we can design interpretability into an end-to-end motion planner. So in this section, we're going to go over a couple of papers in a little bit more details just to illustrate the different themes for incorporating interpretability into end-to-end motion planning. And we'll start with the neural motion planner. So the high-level idea behind the neural motion planner is we're going to predict this planning cost volume directly from raw sensor data. And then using this cost volume, we can then sample a bunch of trajectories, cost them, and use a minimum cost trajectory to execute, right? So here's how the model kind of looks like. We'll start with first taking raw LiDAR and HD maps in and extracting some features. Then using these features, we're going to predict three things. We're going to predict detections, predictions for how the agent, how each actor would move over time, and then also a planning cost volume. So as I mentioned earlier, each voxel in this cost volume represents the cost of the self-driving vehicle being in a particular location at a particular time, right? So given this cost volume, we can then sample a set of diverse, physically feasible trajectories from the current SDV's pose, right? Then we can cost each of these trajectories by indexing into the cost volume at each waypoint along the trajectory. And then finally, we just select the minimum cost trajectory to execute. So note that all of this can be done in parallel. So planning should only take a few milliseconds to complete, right? So here's a short video illustrating how NMP works. So we have LiDAR, HD maps, the model does perception and prediction. And then now we're visualizing the low cost regions with different colors representing different time steps. And the planned trajectory here is shown in red. So from some of these qualitative examples, you can see the model has sort of captured following or lane following pretty well. In some cases, you will actually see the cost volume capturing multimodality as well. So for example, here we have intersection, and you can see that the cost volume assigns low cost regions to both turning right and going straight, right? And we can also handle blockages with this approach. So the cost volume would sort of show a preference to lane change or to nudge around heavy traffic in order to avoid collision while still making progress. Cool. So there are still some shortcomings with this approach. First of all, planning is not explicitly conditioned on prediction, which might result in inconsistent and dangerous driving. And second of all, the model only predicts a single mode future, right? But the future we learned from the previous session is actually quite uncertain and quite multimodal. So in this follow-up work called DSDNet, we address this issue using a deep structured self-driving network that jointly reasons about perception, prediction, and planning. And now with this network, computation is then shared across modules. We explicitly model socially consistent multimodal futures into the uncertainties into the future. And then the planner can then leverage these predictions as well as any prior knowledge to plan a trajectory to avoid collision and drive safely, right? So here's how it works. As with NMP, DSDNet first extracts some features from LiDAR and HD maps and then produces these bounding box detections. Then in order to predict socially consistent multimodal trajectories for the other actors in the scene, we'll first sample a set of diverse physically feasible trajectories for each of the actors in the scene. Then we'll perform some message passing in between each of these actors in order to obtain socially consistent multimodal predictions. And then finally, to plan the SDV's trajectory, we do sort of the same procedure as in NMP. We sample a set of trajectories, cost them, and pick the minimum cost trajectory. All right. Now, let's take a look at some qualitative results. So here we're visualizing the uncertainty of the actors' predictions over time, and different colors show different times. So here's 1 second, 2 seconds, and then at 3 seconds, you can see sort of like the multimodality of some of these predictions, right? Now, if we take a look at this demo, you'll see, again, the predictions of the model capturing multimodality very well, right? And in red here, we have the self-driving vehicle, and it's planning to avoid these, or planning to avoid collisions based on the predictions of these actors. Cool. Okay, so up to this point, the end-to-end motion planners that we've discussed first detect objects in the scenes, then predict their future trajectories, and then plans a safe trajectory to avoid collisions with them, right? Now, this pipeline works great, so as long as your detection module is working as expected, right? But what happens if, for example, the detection score flickers a little bit, and all of a sudden you don't see this like oncoming actor anymore, right? So in some cases, this could be catastrophic, right? You might just run into this actor because you don't see him anymore. So in this next work, P3, they propose an approach to address this issue. So rather than performing object detection and then predicting trajectories for each of these objects, this model instead directly generates semantic future occupancies, right? These occupancy forecasts are scene-based and instance-free, so we don't need to rely on things like thresholding a detection score to get rid of false positive detections or performing NMS post-processing in order to sort of reduce redundancies in the detections, right? So now, as a result, even if your detections, even if your model is a little bit uncertain about the detection, right? You don't run into the risk of misdetecting an object, but instead that uncertainty is directly baked into the occupancies themselves, right? Then the planner can then use these spatial temporal occupancy maps as well as other interpretable costs in order to plan a safe trajectory, to execute. And because the entire model is differentiable, you can actually train the model end to end. Cool. So let's take a deeper look into the semantic occupancy representation. So the model considers vehicles, pedestrians, and bikes as different classes. And within each of these classes, we actually further subdivide them semantically, right? So for example, for any pixel of interest, the model would predict how likely it is to be occupied by, say, a vehicle on a conflicting lane or a parked vehicle or maybe even a pedestrian, right? And this sort of like hierarchy allows the motion planner to then behave or learn to behave differently around different kinds of road users. For example, for VRUs or vulnerable road users like pedestrians and bicyclists, you would want to behave a little bit more cautiously around them, right? And then to predict these occupancies, the model first extracts some features from LiDAR and HD map input. Then it uses a recurrent occupancy update network to predict these occupancies into the future. Then given these predicted occupancies, the planner will then, again, sample a bunch of trajectories, cost each trajectory according to a set of interpretable cost functions, and then pick the minimum cost trajectory. So the cost functions that we can use here include cost functions for safety. So for example, to encourage the SCV to avoid the occupied regions that were predicted. Cost functions to encourage comfort and following traffic rules, and cost functions to encourage route following, right? And importantly, the relative importance of all of these cost functions or subcosts can actually be jointly learned with the rest of the system. And then here is just some qualitative results seeing P3 in action. So the solid black box is the planned trajectory that of the SCV going into the future, right? And the different semantic layers are predicted by the model are shown in different colors here. Yeah. Moving on. So one of the disadvantages of P3 is that it predicts these explicit discrete occupancy grids, right? So this could incur discretization error, and it's also computationally expensive since we will need to predict large grids of occupancies over time at a sufficient enough resolution that you can actually see and avoid small objects. So, however, at the same time, planning only really cares about occupancies around where the SCV might actually reach. So we don't really need much of the occupancy grids that we've predicted, right? Therefore, instead of predicting an occupancy grid, can we instead only predict occupancy at continuous space-time locations for the trajectories that we actually need to cost, right? Sergio talked a little bit about how we can actually do this in the previous session. So in this session, I just want to quickly cover a work that extends P3 by replacing the explicit occupancy grids with an implicit occupancy function instead, right? And now with this approach, you reduce the amount of redundant computation you need to do, and it makes the overall system much more efficient and practical to run. And then finally, we've seen a couple ways in which end-to-end motion planners can take advantage of sort of structured and interpretable costs for planning. And this allows us to encode prior knowledge about what constitutes good driving much more easily. And it also has really, really well-defined intermediate supervision, right? Making it easier to train. We've also talked a little bit about how we can use unstructured costs to capture implicitly many other aspects of driving that we might not have encoded through explicit structured costs, right? So the question is, can we combine these two different ways of costing? So we can then have structured costs in order to encode our prior knowledge, right? And unstructured costs to capture everything else that is either too difficult to express in the unstructured costs or that is left out, right? So there's been a couple of recent papers that do exactly this. For example, STP3 on the right there. And basically, it just learns to combine these learned costs with rules-based costs in order to learn more capable planners. Okay, now switching gears a little bit. Up to now, we've seen a couple methods, or all of the methods we've seen require HD maps as input. And as I've mentioned earlier, HD maps are actually a really, really great prior for planning. However, in order to use this map, we actually need to accurately localize the SCV onto the map. But what if localization fails? Or what if it makes like a small mistake, right? Or there's noise in it? Then in this case, you might actually run into some catastrophic consequences. For example, as illustrated here, the SCV might actually end up taking the wrong path and driving into opposing traffic instead, right? Besides this, HD maps are just more expensive to annotate and hard to scale, right? So on the other hand, if we were able to do mapless driving instead, then we impose much fewer requirements, right? And this approach is much more scalable because now we don't need to map everywhere we need to drive. So this next work, MB3, proposes a way in order to do mapless driving. So as MP3 receives LiDAR data as input and predicts occupancies over time. However, now MP3 doesn't have access to the HD map, so it will instead predict an online map to be used for planning. Then, given these intermediate representations, the planner will then predict a route given a high-level goal like turn right or lane follow. Then it will sample a bunch of trajectories, cost them using interpretable cost functions, and then pick the minimum cost trajectory to execute. If we take a closer look at MP3's intermediate representations, you'll see that as a part of its online map, MP3 would predict the drivable region, intersections, and also the lanes that the SCV can legally reach. MP3 will also predict occupancies over time as well as their corresponding motion fields, right? And then given the predicted online map and a high-level command coming from sort of like any off-the-shelf navigation system, right? We can then predict the desired route as a dense spatial map using the sort of like switch of CNNs here. So for example, when the command is turn right in 50 meters, right? The output would be this green route shown in the image here. Another challenge we have is how to actually generate trajectories for the SCV. So in traditional planners where you have access to the HD map, we can, for example, use lane relative samplers in order to generate trajectories that lane follow or lane change, right, with some variations. But in this mapless setting, all we're given is the current state of the SCV, and we don't know where we are in the map. So how can we actually generate these trajectories? So to work around this issue, MP3 will instead retrieve trajectories from a data set of expert trajectories and then use those as candidates instead, right? Now, of course, these trajectories need to be conditioned on the SCV's current state. So MP3 will sort of retrieve different sets of trajectories based on the SCV's initial state as shown here. Finally, as MP3 will cost each trajectory and pick the minimum cost trajectory for execution. And in MP3, the cost is composed of a set of interpretable subcosts, including subcosts to encourage safety with respect to the predicted occupancy, another subcost to predict safety with or having a safe headway with respect to your lead actor, right? And then some subcosts to just encourage that you stay within the drivable region on the reachable lanes and that you're staying on route. Yeah. And then again, as MP3, the relative importance of these subcosts can then be learned end-to-end with the overall system. Here is a visualization of MP3 in action. So these are actually closed loop simulations. So you can see like what the planner actually executing what it plans to do, right? So in blue, what we have here is like the actual plan of the SDV and what it's doing. And in black, we have the expert human driver from the log. Yeah, so as you can see, like if the command is turn left, you can see this really interpretable like green route, which basically encourages the SDV to take a left turn instead. And then in this particular example, I think we'll see like a pedestrian that's heavily occluded, but MP3 will still predict occupancies for that trajectory or for that pedestrian. And the SDV will then plan a maneuver to act a little bit more cautiously around them. Cool. All right. Finally, let's cover a little bit about reactivity. So since the SDV is a participant in traffic, its actions sort of affect how other actors behave in the future, right? And in turn, how other actors behave in the future will then affect how the SDV will want to plan its decisions or plan its maneuvers, right? So this creates a really, really complicated reasoning chain. And to see why it's really complicated to handle, right? Let's take a look at this T intersection here as an example. So if we were to just consider the marginal distribution over futures for the two actors in the scene, right? That it's really hard to predict or plan a good trajectory because this will basically mix over the possible different futures. Now, on one end of the spectrum, right, if you were to decompose this, you can see, for example, maybe in this first future, the right vehicle or rightmost vehicle will yield to the SDV and then make its left turn after the SDV passes, right? So in this case, the vehicle reacted to the SDV's intended plan, and thus the SDV was able to pass the intersection without hesitation. But so this brings us to the first challenge, right? actors' behaviors can actually vary a lot based on what the SDB plans to do, right? And then on the other end of the spectrum, there could be some cases where the rightmost car actually ignores the SDB and just proceeds with a left turn, irrespective of what the SDB does, right? These situations are less likely to occur, but they're not impossible. And so we want to be able to ensure that we can plan safely in these low probability events as well. So let's take a look at different ways to address each of these challenges one by one. First of all, to consider the reactiveness of each actor, a naive solution is to just sample a bunch of SDB trajectories and then conditionally predict what other actors would do based on each of these trajectories. This is a really straightforward solution, but it's really computationally expensive, right? So how can we make this more efficient? One approach is to implicitly model the interaction between the SDB and other actors using tensor fusion. Or we can actually use more explicit approaches. For example, on the right, using a deep structured model where the pairwise interactions between the actors and the SDB can be modeled with pairwise energies. Yeah. Okay, moving on to the next challenge. The other challenge is how to deal with very unlikely events, right? So previous planners have tried to find a single trajectory that performs well across all possible futures. But since the future is dominated by very high probability events, the planner might be encouraged, for example, to just plan a trajectory that continues straight through the T intersection here. However, this could be unsafe if unlikely events happen, like what we talked about on the right-hand side here, right? On the other hand, if the planner can also be very conservative, so it can take a braking maneuver instead. And while this could be very, very safe with respect to both futures, it's actually overly conservative and might actually result in some uncomfortable or socially confusing driving for other actors in the scene. Yeah, so one paper called Lookout proposes the following approach to solve this issue. So it leverages the idea that we can replan every time we see that there is new information available, right? So instead of committing to a single trajectory now, we'll first choose a single immediate action that we want to execute right now. And then we'll postpone committing to a single long-term action to the future later. So instead, we'll consider a set of long-term actions to react to all possible futures instead. So to achieve this, we'll first sample a bunch of short-term trajectories or short-term actions. And then for each of these actions, we can then sample possible long-term future trajectories that correspond to various behaviors. Yeah. And then to select the best trajectory, we will then cost the sample trajectories based on the following intuition. The immediate action that we want to take should be safe with respect to the worst case prediction, right? And then the long-term action that we take, the cost to go, should not be overly conservative. So as long as we can safely react to every possible future out there. So to illustrate how this looks like, let's see an example. So here we can see an example where it's the same T intersection. And if the SDB continues with its current speed, right, we can successfully pass this intersection in the future. However, now if we consider the other future in red, we'll actually need to perform a hard brake to avoid this low probability event should it happen. So overall, this approach to planning is very unsafe, right? So this short-term action is not what we want. Now, instead, if we slow down a little bit as our short-term immediate action, we can still cross the intersection safely and comfortably in the first future. But at the same time, should the second unlikely future occur, we can still comfortably brake in order to avoid collision as well. So then using the intuition for costing that we discussed earlier, this second action would be the preferred action that we take, right? So here is just, here is just a quick video showing how this sort of lookout planner works in closed loop simulation. And in green, you have the SCB, right? And other vehicles are in blue, pedestrians are in pink. Cool. Yeah, so that wraps up the motion planning section. And then finally, we're just going to really quickly discuss some of the main approaches to controls. So what is controls? The job of the control module is to track the motion planner's trajectory by issuing commands to steering, throttle, and braking, or to those actuators. One way to do this is using optimal control. So for example, in model predictive control, we're going to try to find a sequence of actuation commands that optimizes a cost function based on things like tracking error and ride comfort, right? And we also need to add constraints to this optimization problem in order to account for actuator or system limits. Now, the strength of this approach is that the commands that we issue account for actuator and system limits, thus ensuring that we can track the trajectory well. And we can also ensure ride smoothness and comfort by adding constraints on jerk and steering rates here. The downside of this approach is that it's often slower than other methods, right? It can be hard to tune the objective function that we optimize. And it can be hard to debug at times as well because we're leveraging a black box optimizer here. And then finally, of course, we need to have a very good vehicle model in order to get good results from this approach. So another option is feed forward, feedback control. So here, the feed forward section part sort of generates a sequence of controls that tracks the reference trajectory, assuming our vehicle dynamics model is perfect, right? And then the feedback part then uses observed tracking errors that are caused by any potential discrepancies between our model and the real system, and uses that to adjust the controls so that we're tracking the trajectory better, right? Now, strength of this approach is it's simple to create, debug, and maintain. All right, it's fast to run and it has deterministic computation speed because we no longer need this optimization in the loop. Tuning is also really intuitive if we make use of something like a PID controller, for example, in the feedback part, right? And then finally, this method has been proven to work across like many practical applications already, right? Some downsides of this approach is that feedback only works well in linear regions. It doesn't account for system or actuator limits, and there's no look ahead when we're planning the controls. Cool. And then finally, last topic I want to touch on is actuators. So the controller so far would only output steering and acceleration commands, but we still need a way to translate these into actuator commands. For example, like how much pressure you want to exert on the brake, right? And these actuators need to be characterized in order to have more accurate tracking and in order to understand what is actually achievable by the controller. And some of those important limits that we need to characterize is, for example, for each speed of the SCV, what's the maximum acceleration it can actually do, right? What's the maximum deceleration of the self-driving vehicle, or what's its maximum steering rate, etc. Yeah, so I think that's it for this session of motion planning and controls. We've covered a lot of ground on how to actually learn an interpretable end-to-end trainable motion planner, and we've covered some of the basics of controls as well. Yeah, that's it.
We have time now for a few questions. We will come back at 1:20. So we'll have a little bit of an extra 10 minutes compared to what was in the original schedule, just to make sure people have enough time to grab lunch and everything. So we'll continue back at 1:20 to look at intelligent data mining, data engine, stuff like this. And then we'll talk about vehicle-to-vehicle communication and then all the simulation stuff. Yeah, so there was a question?
So in your Mapless thing, right, you have a goal. So you said go left to right, they could give you accordingly. But what happens if the intersection is complicated? There are multiple levels, multiple rights. How does it decipher where to go?
Yeah, I think that would require like extending the model. Right now, the routing module only considers like some 3 commands, right? Go left, go straight, turn right. I think you can definitely extend the routing module to something a little bit more complicated in order to handle that kind of topology. But that's just not something considered in that paper at the moment. Yeah.
Hello. So, it's regarding the safety. Now, when we for the architecture itself, understanding the planner itself, depending on the previous the prediction and the feedback, the output from it. So, what happens if they have a problem?
Yeah, no, I think that's a really great point, right? Like if in those modular systems, if perception fails or prediction fails, right, the errors can sort of cascade down the pipeline and compound over time, and it could have very catastrophic failures, right? I think in some of the more recent works I presented here, for the idea is that we can still sort of maintain this sort of modular system, but now we can significantly broaden the interfaces between the systems so that the uncertainty of those systems can be propagated through the system down into like motion planning or controls, for example, right? So, for example, if you were uncertain about like some actor because it was occluded, so your detection scores are really low there. In a previous pipeline, you might actually just drop those detections and consider them as false positive detections, which could be very unsafe, right? Now, if you were to instead use something like an occupancy-based representation, right, you can then, instead of saying there's no prediction there, you can express things like, I believe there's a 3% chance or a 30% chance that there is an actor there, and there's some probability that it's going to cut into our driving path in the future, right? And by having this sort of like uncertainty propagate down into motion planning can then safely plan to handle that situation. Does that answer your question?
Kind of.
Kind of.
Because is that someone?
So I think now that like you said, there's not a clear-cut boundary between like perception, prediction, and right. It's they're all neural nets, but at the end of the day, neural nets connected with neural nets, right? I mean, how do you really go about training the weights? Because earlier you had like one goal, right? For perception, you had like one loss function you were trying to tune for that loss function, right? Later prediction, we're trying to tune for that loss function. But now the real loss is on the planning side, basically, right? How do you like train all these units that are like intertwined and connected with each other based on that very loss at the very end, basically?
Yeah, I think in some of the approaches I presented today, what they found was that you actually can't just train only on the end task if you want these interpretable representations, right? It's actually really helpful and really important to also supervise the intermediate tasks as well. So in a lot of these papers that I presented, they would either sort of add these auxiliary tasks or add intermediate supervision in addition to the end task supervision as well. And then for actually propagating the planning loss down through the rest of the modules, right? But because the entire system is differentiable, you can actually just compute gradients of that loss with respect to the entire system and optimize it in that way. Yeah.
Just
quick question. So in a lot of the neural motion planners, the prediction is quite good in at least the simulation. Is there a specific model that you chose to use, or the prediction of other objects?
Oh, in the neural motion planner?
Yeah, sure.
Yeah. So I want to clarify that it's not my work. This is work I'm presenting, but yeah, I believe they use a sort of just a custom CNN based architecture with like I believe it's like a almost single shot detection kind of a training objective at the very end in order to train the detections. Yeah.
So back to the architecture decision. I remember your slide at the very first beginning. There is one, basically, we have multiple stage, the multiple components in the object design. And at the beginning of your slide, you have say end-to-end, which one component end-to-end. So I'm thinking just could be a research, just saying, let's train as end-to-end, because we have only one loss function could be, and that can handle this case itself. In the middle, we'll say these two like a simple model. And with this one to end-to-end training, and does it consistent with multiple components?
I see.
Division. And if they are disagreed with a certain high risk, then there may be something like a problem there.
I see. Yeah, that makes a lot of sense. Yeah. And I think that's consistent with like what some of these papers have found too, right? You need that intermediate supervision, whether it's like with a direct supervision, or if I'm understanding you correctly, like trying to use like the discrepancy between how you imagine those intermediate representations to interact with the final plan, and use that as a training objective as well. Yeah.
I was thinking just architecturally, because I see the earlier, you basically very, if my understanding your slide thinking is that kind of end-to-end training is very hard to integrate or to understand what is happening. But that gives us, I think that the benefit itself is really could be one consolidated object function to optimize.
Yeah.
And that, well, maybe will be solving the risk or mitigate the risk if we optimize an individual component. End of the day, this optimization strategy, maybe it's not done together. End of the day, we could have some risk because individual components will be shared. If we have this end-to-end training symbol or another way to viewing the planning, then they could be mitigating some of the risk.
Yeah, I definitely agree with you. Yeah. Yeah.
Interesting research.